Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. For the state of stress shown, determine the principal stresses and B, the maximum in-plane shear stress. Show the results on properly oriented elements. So here's the given figure. We first plot sigma x comma tau xy, which is positive 28 comma positive 42. And we plot sigma y comma negative tau xy, which is negative 56 comma negative 42. So each grid is 25 megapascals. So 28 would be here, positive 42 would be here, and the other one negative 56, then negative 42 shown. Then the MOHR circle, this is the x-axis, that's the y-axis. Then 2 theta p1, this angle. Sigma bar is equal to 28 plus negative 56 over 2, so negative 14 megapascals. So R is square root of 14 plus 28 square plus 42 square. Sigma bar is 14 plus that one 28. So 28 plus 14 quantity square plus 42 square. So R is 59.4 megapascals. That's R. Then this is sigma P1, sigma P2. So sigma P1 is sigma bar negative 14 plus R plus 59.4. So sigma P1 is positive 45.4 megapascals. Sigma P2 is sigma bar negative 14 minus R. So negative 14 minus R to the left. So sigma P2 is negative 73.4 megapascals. Then we already computed tau max, which is R. The maximum in-plane shear stress is R, is 59.4 megapascals, and it occurs here. So from the principal axis, 45 degrees, 90 degrees in the MOHR circle to locate this axis here of maximum shear stress, where the normal stress is sigma bar, but in the element it's only 45 degrees. So let's solve for 2 theta p1. Tangent of 2 theta p1 is 42 over 28 plus 14, or 14 plus 28. So theta p1 is 22.5 degrees because 2 theta p1 is 45. So theta p2 is 22.5 plus 90, so 112.5 degrees. So this is the element rotated counterclockwise from the x-axis to locate the principal axis 1 as shown. Then on the principal axis 1 acts tension 45.4 megapascals. Then from the x-axis 112.5, that's 112.5 degrees counterclockwise, acts compression 73.4 megapascals, and there's no shear stress because we show the principal axis. On this axis here, where the stress is normal stress and the in-plane shear stress is maximum, this axis here, positive. So remember that the angle between the principal axis and the axis where shear plane maximum shear stress occurs is 90 on the Mohr circle but 45 in the actual. Since this is already 22.5 and that's clockwise direction, so 45 degrees minus 22.5 is 22.5 degrees also clockwise from the x-axis to locate the axis where in plane shear stress is maximum and the normal stress is sigma bar. So that's also clockwise 22.5. This 22.5 is 45 minus 22.5 because this is the principal axis 1. To locate this axis here where maximum in plane shear stress occurs, so we rotate on the Mohr circle clockwise 90 degrees, but their actual angular spacing is 45 degrees, half of 90 degrees. So clockwise, so from here clockwise 45 degrees, so this is 22.5 degrees. So and this is the axis here where maximum in plane shear stress occurs. So the normal stress is sigma bar 14 compression as shown, and the shear stress is in plane shear stress is maximum positive, so up to the right, and it is 59.4 as shown. The rest will follow. So that's it for this problem. For the state of stress shown, determine the principal stresses and be the maximum in plane shear stress. Show the results on properly oriented elements. So here's the given figure. We plot sigma x comma tau xy, which is positive 30, positive 90. And the other endpoint is negative sigma y comma negative of tau xy, negative 60, negative 90. Negative 60 comma negative 90. So assuming its grid again is 25 megapascals, so positive 30 comma positive 90 would be up here. Then negative 60 would be here, comma negative 90. There. Negative 60 comma negative 90. Then the Mohr circle. This is the first point plotted, so this is the x-axis and that's the y-axis. So sigma bar is equal to 30 plus negative 60 over 2. So it is negative 15 megapascals. Then this is the radius, square root of 15 plus 30, so 45 square plus 90 square. So the radius is 100.6 megapascal. Sigma bar 15 plus 30, so 45 square to 45 square plus 90 square. So 100.6 megapascals. So that's the radius. This is 2 theta P1. And this is sigma P1, sigma P2. So sigma P1 is sigma bar negative 15 plus R plus 100.6. So sigma P1 is equal to 85.6 megapascals tension. Sigma P2 is sigma bar negative 15 minus R minus 100.6. So sigma P2 is negative 115.6 megapascals. Then maximum in plane shear stress is the radius 100.6 megapascals. So tangent of 2 theta P1 is 90 over 45, 15 plus 30. So theta P1 is 31.72 degrees. Then theta P2 is plus 90, 121.72 degrees. So let's now show it on the sketch. So the element is rotated 31.72 degrees counterclockwise to locate the principal axis 1, and that's principal axis 2. On principal axis 1 acts tension 85.6 megapascals, and here compression 115.6 megapascals. Then on this axis here, which makes 45 degrees from the principal axis, and since this is already 31.72, to locate this axis here where in plane shear stress is maximum and the normal stress is sigma bar, from the principal axis we rotate clockwise 45 degrees. So 45 degrees minus 31.72, so this is already 13.28 degrees. 13.28 degrees clockwise from the x-axis plus 31.72 is 45 degrees. Remember, in the MOHR circle they are 90 degrees apart. In the actual element, 45 degrees apart only. So on this axis here, acts normal stress of 15 megapascals compression as shown. Then the maximum in plane shear stress of 100.6 positive, so it is up to the right as shown, and the rest will follow. So that's it for this problem.